Hello and welcome back. So today I'm going back in the office for the first time in like 2 years. Despite how horrible COVID is in Florida, we are teaching face to face. Well, seatbelts on and let's drive.
So today I want to talk to you about compact operators. These are the special operators where you can approximate them in the norm topology with finite rank operators. And this has an especially large bearing on dynamic mode decomposition, where all of our algorithms depend on finite rank operators that come from data. So today we're going to also talk about the spectral theorem for compact self-adjoint operators, which will set us up for all the convergence results and other things that we want to talk about later. And we also have a new operator that I would like to talk to you about, and that is scale Liouville operators, or Liouville weighted composition operators.
Back in my office, and looks like I have a lot of packages to go through. So I've gotten kind of spoiled by working in my home office for a long time, so this whole commute thing and getting into work and walking upstairs and going to my office seems really foreign. There's this huge desk here, but it takes up a lot of space, and I want some room to move around. So, if you've taken linear algebra, then you probably have some idea of what a linear transformation is. It's basically an operation where the distributive property holds. And we know that for any linear transformation, we have a matrix. Everything about a finite dimensional linear transformation is encoded in its matrix. However, when you get up to infinite dimensions, it doesn't work nearly as well. You see, for infinite dimensional spaces, there's whole new problems that you run into, and the matrix doesn't always represent the operator as well as you think it would. How well this matrix will represent your linear transformation very much depends on the linear transformation itself. If it's a bounded operator, then as long as you have the full infinite dimensional matrix, then it's a good representation of the operator. But in reality, in any sort of data setting, we're only going to have a finite piece of that matrix, and we want that to be able to represent our matrix, especially in this sort of data-driven DMD setting. And so for that sort of thing to work, we need something that's called a compact operator. You think these are still good after 2 years? I don't know. So before we talk about compact operators, first we have to talk about topologies and what does it mean to converge. So right now, the best convergence result that we have for dynamic mode decomposition comes from Korda and Mezik's work, where they showed that the finite rank operators that you make for DMD converges to the Koopman operator in the strong operator topology. Now, this is great for the Koopman operator and finite rank operators, and it's a really nice result. But at the same time, it isn't good enough. And the reason why is that strong operator convergence does not necessarily guarantee convergence of the spectra. And so we need something better than this. And what we're going to be turning to is the norm topology for bounded operators. But before we can talk about norm topology, we have to actually talk about the norm. So what is a norm exactly? A norm for an operator, say T, is a limit on how much that operator is going to be stretching an observable, or a member of your Hilbert space. You can define exactly what this needs to be by taking a look at T operating on some arbitrary G out of your Hilbert space, taking the norm of that, and then dividing by the norm of G. If you take the supremum over all G inside of your Hilbert space, this gives you the most that an operator can stretch a vector. If the supremum ends up being bounded, then we say that T is a bounded operator, and we call that supremum the norm of T. What this does is it actually gives us a metric on the space of all bounded operators, where we can define a distance between two different operators, say T and W, by taking their difference and then looking at this norm. A compact operator is an operator T that admits a finite rank approximation according to the norm topology. And what that means is that there's going to be some sequence of finite rank operators, or say matrices, that will converge to your operator T according to this norm. And since DMD is all about making finite rank operators from the data we observed, we really need that our limiting operators be compact. So what I'm going to do now is I'm going to show you the spectral theorem for self-adjoint compact operators. And after that, I will show you a compact dynamic operator that gets us really close to solving this whole convergence issue. And in subsequent videos, I'll show you how we can really clinch all of this. Let's go ahead and get started.
So here's the setting. We are trying to prove the spectral theorem for self-adjoint compact operators over a Hilbert space. Remember, every Hilbert space has an inner product, and an operator is self-adjoint if whenever you take two functions in your Hilbert space, say g and h, then write the inner product as a of g, inner product with h, the operator can then be moved from the left to the right as g inner product with ah. An eigenfunction of an operator is a function phi, such that a times phi is equal to lambda times phi for some lambda that may be a complex number, and we require that phi be non-zero. I use the term eigenfunction here a lot, but you can also think of this as an infinite dimensional vector. We use the terminology eigenfunction when our space consists of functions. Our goal is to find an eigendecomposition of our compact self-adjoint operators, which means that we are looking to diagonalize an infinite matrix by finding a basis of H consisting only of eigenfunctions. For a moment, let's consider two eigenfunctions, say phi and psi, with eigenvalues lambda and mu, respectively. A nice property about eigenfunctions for self-adjoint operators is that the eigenvalues are all real valued, and those eigenfunctions corresponding to different eigenvalues are orthogonal. To see that the eigenvalues are real, note that the inner product of a phi with phi is equal to just lambda phi inner product with phi, and then we can pull that lambda out, and that leaves just phi inner product with phi inside the inner product. But also, we can move a to the other side. So we can write a phi inner product with phi as phi inner product with a phi, because a is self-adjoint. And then phi is now inner product against lambda times phi. And now, since we're trying to pull lambda out of the other entry of your inner product, that means that lambda comes out as a lambda star, or a conjugate. And since we have phi inner product with phi on both sides here, we can then divide those out, since phi is assumed to be non-zero, and now we're left with lambda is equal to the conjugate of lambda. And well, the only time that happens is when lambda is real. Now, as far as the orthogonality between, say, phi and psi, it follows like this. Again, we start with a times phi is inner product with psi, and then we use the eigenvalue property, and so we can pull out that lambda, and then we're left with lambda times phi inner product with psi. Now, on the other hand, we can move a to the other side of this inner product, because a is self-adjoint. And so then what we get is that this could also be written as mu times phi inner product with psi. We have that lambda times phi inner product with psi is equal to mu times phi inner product with psi. Psi. I'm having a lot of trouble saying psi for some reason. In any case, so we can move all these over to one side, and we see that we have lambda minus mu times that inner product is equal to 0. So either lambda minus mu is equal to 0 or the inner product is equal to 0. But we know that lambda and mu are actually different, so their difference cannot be 0, and that means that this inner product has to be 0. So these two eigenfunctions with differing eigenvalues turned out to be orthogonal, and so that's really nice. So now let's take a look at this whole eigendecomposition idea. For each eigenvalue, the collection of eigenfunctions corresponding to that one particular eigenvalue, we're going to group them all together, and this space is going to be called an eigenspace, and we will denote this by E lambda, where lambda is our eigenvalue. Now, what we have just shown is that these eigenspaces corresponding to different eigenvalues are orthogonal to each other. Hence, if we can leverage our matrix intuition here, going back to 101 linear algebra, we know that if we had two subspaces that were orthogonal to each other, then we can write their matrix as a block diagonal, and that same sort of idea happens here. If A can be decomposed into collections of eigenfunctions, then we can use the self-adjointness in order to show that each of these eigenspaces can be grouped together and make a block diagonal, where possibly each of these pieces might be infinite dimensional. But we'll see that that can't be the case later. At this point, we have yet to use anything about compact operators. We have only used self-adjointness. An equivalent characterization of compact operators is that for every bounded sequence of functions inside of the Hilbert space, the mapping of this sequence has a convergent subsequence. As long as we are working with Hilbert spaces, this is equivalent to an operator being approximable by a sequence of finite rank operators. But this Equivalence is lost for Banach spaces. This is an important distinction where our application idea is in DMD, which happens exclusively in the realm of finite rank operators. So I guess it's a good thing we are working with Hilbert spaces. So the first question we have to ask is if there are any eigenfunctions for A at all. And the answer, as you may have guessed, since we're making this video, is yes. In fact, one eigenvalue for A is equal to plus or minus its norm. Suppose we had a sequence of functions, say gm, in our Hilbert space, each of which has a unit norm. And we'll assume that the sequence has a property that if you were to take A and apply it to gm and inner product that with gm, take a look at this absolute value, then the limit of that sequence of real numbers will converge to the norm of A. We know that such a sequence exists by the definition of the norm of A. And moreover, we can see that if we take a look at A gm inner product with gm, then we can move A to the other side of that inner product, and then we can swap those two entries around and use the fact that if you exchange the two entries of inner product, you get a conjugate. We see that AGM inner product with GM is actually equal to its conjugate. So we see that all of these entries in this sequence of numbers are all actually real valued. And as such, this sequence of real numbers is either clustering around plus the norm of A or minus the norm of A, or possibly both. And so what we can do is we can replace AGM inner product with GM with a subsequence that is converging to one or the other, so we'll just ignore the other guys. And we will write C as either plus the norm of A or minus the norm of A. And the C will eventually become one of our eigenvalues. Let's also note that since GM is a bounded sequence and A is supposed to be a compact operator, there is a subsequence of AGM that converges. And so we'll go ahead and replace the sequence of GM with that corresponding subsequence that converges under A. We will use this later to show that GM itself actually converges. Now let's consider the difference between AGM and CGM. And ultimately what we want is we want to find a G such that AG is equal to CG. But we aren't there yet. So what we're going to do is we're going to take a look at the difference between AGM and CGM. We're going to take that norm and we're going to square it. What we can do then is we can take the expression of the norm in a Hilbert space as coming from an inner product, and so now we have the inner product of AGM minus CGM with itself, and then we can use the linearity properties of inner products, and ultimately what we end up seeing is that we end up getting the norm of AGM squared minus 2 times C times the inner product of AGM with GM plus the norm of GM squared. Now recall that the norm of GM is just 1. That was part of the definition of GM. And that we have already shown that AGM inner product with GM goes to C. And finally, since C is equal to plus or minus the norm of A, we know that the norm of AGM squared is less than the norm of A squared, which would be the same as C squared. And this comes from the definition of the norm of an operator. Thus, the right-hand side of this equation tends to 0, and the norm of AGM minus CGM converges to 0. But as AGM is a convergent sequence, that means that CGM, and hence GM, is a convergent sequence as well. Hence, there is some G such that GM converges to G, and consequently, AGM converges to AG. And that means that AG must be equal to CG. And G is an eigenfunction for A with eigenvalue C. And this whole little lemma we have here is the essential bit where compactness comes into play. So now let's talk about the spectral theorem for compact self-adjoint operators. And let's start with the statement. Let A be a compact self-adjoint operator on the Hilbert space H. Then the family of eigenspaces, say E lambda, where lambda ranges over all eigenvalues, is an orthogonal decomposition of H. To prove this, we start by taking the closure of the span of all E lambdas, and we write this as F. What we want to see is if there's anything left outside of F. And if there is, there should be at least one function orthogonal to f in H. Let's write this collection of all functions orthogonal to f as the Hilbert space H tilde. Now H tilde can't have any eigenfunctions since all of those are in F. Every element of F can be written as a limit of linear combinations of eigenfunctions. Note that A maps F into itself, since if H is in F, then it is a limit of linear combinations of eigenfunctions of A. Then hence A is being applied to H means that A is being applied to a limit of linear combinations of eigenfunctions, but if you apply A to this linear combination of eigenfunctions, then you're going to get a different linear combination of eigenfunctions. And this is going to be taking a limit here, and then this limit is going to reside in F because F was made to be closed. A also maps H tilde into itself. And this follows since if G is in H tilde and H is, say, in F, then G inner product with H would be 0. But also A times G inner product with H is going to be the same as G inner product with A times H. This uses self-adjointness. And since AH is actually in F, which we just established, that means that G inner product with AH has to be 0 because G is orthogonal to everything in F. Hence, if G is orthogonal to F, then so is AG. What does that mean? This means that if we restrict A to H tilde, then the image of H tilde under A is going to be H tilde again, or at least contained in H tilde. And so that means that A is a compact operator from H tilde to itself. Now, keep in mind, H tilde can't have any eigenfunctions, because if it did have an eigenfunction, that eigenfunction should have been in F to begin with. But since A is a compact operator on H tilde, then that means that there has to be an eigenfunction in H tilde for A. Either that, or H tilde is just the 0 function. And so, since we know that H tilde can't have any eigenfunctions, that does mean that H tilde must be just the 0 subspace. And so hence, we have a complete decomposition of H in terms of these eigenspaces. Now we are almost done. We have shown that we can decompose H into a collection of eigenspaces of the compact self-adjoint operator A. And we know that each eigenspace is orthogonal to another eigenspace with a different eigenvalue. This gives us a block diagonal structure to A. But we want two more things. We want each block to be finite, and we want each block to be diagonal. To get each block diagonal, all we need to do is invoke the Gram-Schmidt orthogonalization process, and that's basically where you take a basis for E lambda, and then you start with that first entry in that basis, and then you normalize it, then you go to the second one, you subtract a chunk of the first one to make that orthogonal, and then you normalize, and etc. And then you just continue this process through, and then eventually I'll give you an orthonormal basis. That's sort of a hand-wavy description, but it'll get you there. The finiteness of each block also follows pretty quickly. Note that A maps E lambda to itself, and that means that A mapping E lambda to E lambda is a compact operator. We can use the basis above, and we can look at A as that sequence on this Gram-Schmitted orthonormal sequence of E lambda, and if that sequence is infinite, then that means that A phi m is equal to lambda phi m has a convergent subsequence, but since phi m is an orthonormal basis, each entry in that is orthogonal to the rest, and each is a unit vector. That means that this sequence has no convergent subsequence, and then that would be a contradiction. Hence, each E lambda has to be finite dimensional. And so that means that each block in our block diagonal is a square matrix of finite size. And we are done.
So I think that ends my trip to the office. And that also tells you what compact operators are, and it gives you the spectral theorem for compact operators, which is a nice foothold for talking about things like this singular value decomposition and things like that. Over the next couple weeks or months, I'm going to introduce you to several ways that you can actually get compact operators from the Liouville operator. And the first way is something that my colleagues and I have published, is a scaled Liouville operator. And this is really interesting because what you do is, before you take the gradient and you multiply by f from your dynamics, what you do is you actually compose with a scaling. And so you choose some a with magnitude less than 1, and you multiply it times x. And if you do that, and then apply the Liouville operator, you're going to end up getting that scaling factor a times the gradient of g composed with a times x times f of x. And if you're over the Fock space and your f is a polynomial, it turns out that this is compact. And what's interesting is that this guy also has a nice relationship with occupation kernels. If you take an occupation kernel, say gamma corresponding to your dynamics f, then the adjoint of this operator on that occupation kernel is still a difference of two different kernels, but this time centered at that scaling factor a times the endpoints of your trajectory. And what's significant about this is when you do try to do a DMD type construction, you get almost exactly the same matrix that you would out of the regular Liouville operator. If you choose some compact set, you can make it your A close enough to 1 that you're not actually going to see any difference computationally between the matrix for a Liouville operator and the matrix for this operator. And so, in a sense, the Liouville operator is really, really close to a compact operator, and in fact, this scaled Liouville operator. Now, this is not actually a Liouville operator, so we still have a few things in the way. But over the next several lectures, I'll show you how to make a proper Liouville operator a compact operator. So subscribe, come back, and well, thank you for watching.